kilowatts in the arm?
No.
50 watts.
150 kilowatts in the arm.
Yeah.
In the arm.
150 kilowatts in the arms.
Yeah.
Something like that.
Okay.
Hopefully by the end of the day we'll get it to 200 kilowatts or so.
And how did you guys get to 90 megapascals?
It's just the increase in power.
Oh,
So,
that's okay.
Yeah, it's just the reason we want a high laser power is even though it's a lot of power, it's made up of individual light particles, individual photons, and they arrive at random times, and that produces a noise. So the more you have, the more precisely it can resolve your power. And that's what our readout is at the end of the day. So that's why we're pushing up the laser power. And it worked for a little bit. But
one thing I like to mention since Stefan's here is he was also with me that shift for the first detection. So we were both here that night, and he was busy doing a lot of crazy. He had his hands on the machine, and so I think around 10 p.m. that night is when he handed it over to me, and then at 2:50 in the morning, that's when
you hope you had a quiet night afterwards, right?
Yeah. Luckily we did. At those sites. Okay. Any questions for our scientists?
The seismic tracker?
Oh yeah, so we have the USGS website up there all the time, and the dots on that. Oh, this was the operator on shift for that first detection. That's Annie here. She's a grad student in Australia now.
Yes, I am.
Oh, pardon me. Sorry, you're good.
You're out the LV.
Excellent.
Yeah. Okay. Yeah. So that's just showing us earthquakes over the last 24 hours. So if there's an earthquake that happens in the last hour, you'll see a red dot on there, and then after an hour it'll go orange. So that's a public website anybody can look at. We have our own seismometers right here. And so, similar to that plot over there, on the right side is now, and then we look at the last 24 hours. And so, one thing to look at, for the most part, let's look at the top plot up there. So, most of it is flat, but you can see if you go from the left, if you go this way, around minus 16, minus 14, you can see a bump there. So that bump was an earthquake that happened in the South Pacific, because I looked it up earlier. So that was a magnitude 6 earthquake. Craig might have been on, were you working on the machine at that time? 16 hours ago?
Negative.
Oh yeah, Georgia and I were here.
Yeah.
We didn't.
Is that what?
It was a pretty awesome moment. Like the angular controls of the interferometer were going crazy for about 6 minutes. And it was a pretty big earthquake, so we were very happy that the angular controls were doing so well, because usually as soon as an earthquake hits, we just bam, interferometer's gone. So it was kind of interesting, and it actually allowed us to find some things that we didn't know about apparently.
So, good.
As far as scattered light. So like, because when an earthquake hits the interferometer, it causes all the mirrors to do like this, like crazy, like, and so everything's going everywhere, and the light's going all over the place inside the machine, and so we were able to find some scattered light. Apparently, that's important for us in making the instrument more sensitive.
Nice. Okay. And one thing you'll notice, we all have to walk that tightrope of not using acronyms. So he was saying, he was wanting to say ASC, that's the alignment, sensing, and control. So we have so many acronyms, you need a translator to listen to LIGO speak sometimes.
What's the green clock?
Yes, that's another popular question we get. So our clocks are local time here, and then Greenwich Mean Time or Universal Time Coordinate, UTC, is over there. And then the green one, it was 0 back in January of 1980 when that GPS satellite went online. And so it's been pecking a second at a time, and that's how many seconds have passed since that satellite went online. Yeah. And we need those clocks so that we can all use the same time. So the observatory here, the observatory in Louisiana, Italy, India, will all use the same time. So it'll either be UTC time or GPS time, just so that we're all in the same wavelength.
How much synchronization do you need between here and there?
Oh, it's fractions of a second. I mean, our data has to be very highly resolved. I think.
Outlet.
I don't know. Yeah. We all use atomic clocks to keep the same timing for all the observatories.
You have your own individual atomic clocks, or are you using National Bureau standards?
Yeah, we have atomic clocks, and then we have antennas for GPS too. So I think we use both of those actually. I don't, but I'm not totally sure of all the timing constraints we have.
Are any of your data types or the data that you're collecting dedicated to geological research in addition to physical research? Since you have such sensitive equipment for
I guess that could be a possibility. I mean, once we are shaken to a point where we can't control it anymore, like what Craig was saying, we're offline, so we can't record anything. So our seismometers that we use that are installed